Process capability studies. As the words imply here, we are basically talking about a process, and what is a process? It has input, it has output, it may have sub-processes within it. In fact, there is a very beautiful tool technique which is called the SIPOC. Supplier, the S stands for supplier, I stands for input, P stands for process, O stands for output, and C stands for customer. So SIPOC would give you a complete helicopter view of the entire process. And then if you zoom further within each of those sub-processes, you'll be able to see in detail about how the process flows through different type of activities. And as you know, that in a process, it is an interplay of man, machine, material, method, measurement. That is the 5 M's are very much part of it: man, machine, material, method, and measurement. And as we discussed yesterday, that the process is very well defined by what is called the standard operating procedure. So what is the purpose of a process? To meet its objectives. What could be the basic objective? For a manufacturing process, one of the main objectives is to meet the requirements of the product. So for example, that if you are doing a jig boring, or if you are doing a simple lathe machine, conventional lathe related operation, maybe we are trying to turn a diameter, or maybe you are cutting the length. So if it is a critical dimension, there will be tolerance associated. So our fundamental purpose is that without making any defect, generating any defect, how well we are able to meet the specification. So if the process is able to meet the specification, we call it a capable process. If it does not, we'll not call it a capable process. Now, there are quite a lot of repercussions of not meeting the process as desired. One is that if the process is not meeting its requirement, then the manufacturer would have to do some rework, and in quite a few cases, he has to reject it, and therefore that escalates the cost of the process. So it is very important that right the first time, that is first pass yield, is 100%. And for that, the Six Sigma process, which you have learned earlier, it helps a lot. Because you must have seen that a proper Six Sigma process with 1.5 sigma on the right side and the left side, if it is designed like that, then a Six Sigma process would not be generating more than 3.4 parts per million. That means out of 10 lakh pieces, only 3.4. That means say around 3 or 4 would be at the most going outside the limits. So that means that 100% inspection would be would be impossible, because no 100% inspection has the ability to really detect 3 or 4 out of million, if at all it happens. So therefore, we say that Six Sigma processes, which are highly capable processes, are able to really generate almost 100% defect-free products. So therefore, you don't have to do any inspection. So entire inspection overhead in the form of precision instruments, in the form of the salary and wages of the inspectors, etc., they all can be completely eliminated. So that is how the cost of the process goes down, and therefore the profit margin goes up. Therefore, from that angle, the process capability studies therefore play a very, very important role in all manufacturing, or also even in a service process. So let's dive deep into what is process capability in a more technical manner. So what is the origin of the process capability study? So whenever we take the process capability index, the most conventional one is called the CP. That is called process capability index. Normally, that is the first thing that comes in the mind of people. And I'm very happy to tell you that I met this gentleman in USA in my first visit in 1994. So Dr. J.M. Juran. So Dr. J.M. Juran, his name is taken actually along with Mr. Kane. So Dr. Juran is associated with CP, and Mr. Kane is actually taken for CPK. And there is also another one which was devised almost at the same time of 1986-87, that is called CPM. I'm not going to discuss about that. So, but it is also not very difficult. It is easy to understand. It has a different usage altogether. So, which was independently designed by Siang and Taguchi, again, a great exponent in the field of engineering statistics in 1985, and by Tiang, Sheng, and Swiring in 88 on the same subject. So you must have listened to the day one lecture by Mr. Kirkire when he was talking about the evolution of lean. And in that context, he was also talking about the advent of Six Sigma. You can put yourself in mute, that will help me. In 1986, Motorola developed a statistically based method for performance measurement to reduce variation. And that was the beginning, actually, of what we call in today's context as the Six Sigma concept. And found that quality level correspond to failure rate of 2 parts per billion. So many people get confused that why it is that sometimes they're talking about 2 parts per billion and why it is sometimes being referred as 3.4 parts per million, which I have already explained to you. The reason being is that in case of Six Sigma, we allow a scope of an opportunity of deviation of the target, of the average, around the target by 1.5 sigma on the right side and another 1.5 sigma on the left side. So that much actually, after considering that deviation, the number of products that may be falling out will be around a little more than 2 parts per billion, that is 3.4 parts per million, which can be technically explained also. So these all can be seen in almost any textbook of statistics and statistical quality. Let's try to now get into a dive into the process of understanding capability a little more, and then probably I'll show you a simple case study. And then if you have any question, you can ask me, because then after that we'll get into the completely into the lean methodology. So variation in data forms a pattern. That is the first and foremost, most important. That if the data forms a pattern. So supposing, please put yourself in mute. Yeah, yeah. So suppose we are turning a diameter and we have collected one sample. And let's say that this is the x-axis where the dimensions are written. And then whatever is the size found, we are putting that in the graph, that particular dimension, we are putting that as a symbol like this. And then we collect another sample. And suppose that another sample comes to the right side of the target. Another sample or a couple of samples, maybe they are found to be distributed like this, maybe some more. And if the process runs under chance causes, which you must have learned by now, that what is called chance cause. If somebody has a doubt, you may just raise your hands or ask the question. I will elaborate that. So if the process runs under the chance causes, Navnath Ghule, voice is not audible. You have a problem with chance cause and assignable cause? Yeah, unmute and please speak out. Okay, fine. So I guess that all of you understand what is called chance cause and assignable cause. If the process has been designed in such a manner, the standard operating procedure has been written for the process in such a manner, that is the interplay of man, machine, material, method, measurement system has been designed in such a manner that there is no scope of any assignable cause coming up. The process is completely guided by the built-in factors, which are playing the integral part of formation of the diameter, and they are completely defined in the standard operating procedure, and they would be, all of them would be varying within a certain upper limit and lower limit, and therefore the outcome will be a normal graph. Why we are calling normal graph? The top end of the bars, if you try to connect it, you will be able to find a smooth curve, and that smooth curve, since it resembles the shape of a bell in a temple, so we call it a bell-shaped curve. And because Gauss Gaussian, that is the Carl Gaussian, a German mathematician, who first came up with this definition of this normal distribution. Actually, that made him to get a place within the top 10 mathematicians of all the time in the world. So then he came out that if the number of samples keep on increasing, that means number of sample, if we call it n tends to infinity, and then if we continue to plot the histogram therefore would become, closer and closer and closer, and then ultimately, if you join that, you will get a very smooth line, what is called a normal distribution line. Now, this normal distribution line has certain properties, which some of you who have gone through the normal distribution graphs properties, and particularly the Z scoring method, that is nothing but the standard normal distribution, which is defined by two parameters, the normal distribution. Which are the two parameters? One parameter is called the average or aggregate.
Sorry, may you please go slowly, because it's a very uphill task for, I think, for me to to understand these things. Please go a bit slowly, sir. That will be most kindness.
Okay, I'll try to speak slowly. And but please let me know if certain concept is not clear to you. Then I will also refer to you certain books, certain references,
Sure,
which will make it very clear to you.
Sure,
Okay.
sure.
But now what I'm going to speak is that I'm going to speak slowly, so that I'll give it time for you to understand.
Thank you, sir.
Okay. What I said just now is through the example of a diameter of a part which is being manufactured through a simple lathe machine. And what I said is that if I continue to manufacture and take the dimension of that particular diameter and then try to put the dimension and build the dimension by taking more and more samples from the same process over a period of time, we will come to a frequency diagram which will be looking like this. And that frequency diagram shows certain properties. The properties which were defined by Carl Gauss. Who was Carl Gauss? A German statistician, mathematician. And he proved that if the process operates through number of factors which are controlled and which run through the chance causes, that means those causes which are not assignable, they do not appear suddenly and disappear suddenly. The process lives with those causes. For example, that if you are running a lathe machine, it will have the coolant for which the temperature will slightly increase, sometimes slightly go down. Then there is also hydraulic oil flow, which also will have certain pressure variation. Then we have also, during the turning, there will be certain vibration. The vibration also will be within certain limits, but there will not be a altogether totally sudden random causes appearing and disturbing the process. What could be the sudden abrupt intervention of some unwanted cause? Like, for example, that suddenly you get a particular part coming from your supplier which has a cavity in it. So if it has cavity in it, then you have to stop the process, and because the tool may get damaged, and then take it out. What could be the other thing? Maybe that all of a sudden you find the tool has become blunt, and therefore the tool is required to be dressed. So you replace it. But the part that has been produced by the tool, which was found to be worn out, that caused a defective part to be produced. That is called an assignable cause. So if such assignable cause, which are outside the standard operating procedure, because by standard operating procedure, those causes are unwarranted. They are not allowed to come in. So what I said is that if a process is allowed to run under the chance causes, which are many and which are present in a process, you will find certain variation. But those variations, you can say, they are under control. And therefore, the variation of the part dimension from either side of the averages will be symmetric. So this is called symmetric normal distribution. And that exhibit certain properties. And those properties you can find it very easily in a standard normal distribution table. And what are those properties? The properties are very simple. For example, you will find, now I'm putting the same normal graph the other way around. So if you put the same normal graph the other way around, we can say that standard deviation, I hope all of you know the definition of the standard deviation. It is the all dimensions summed up, average is taken. From the average, if each of the dimension is subtracted, and then you square it up, add it up, divide it, all the dimensions minus 1, that is what is called the degrees of freedom, and take a square root. That is called the standard deviation. Now, you are not going to discuss here why all of a sudden standard deviation. I will only say standard deviation is a very good measure of what is called variation. Okay, so there are other terminologies also for measuring variation. For example, range, maximum minus minimum. But standard deviation mathematically has been found to be the best method for finding out the variation. So if I take one standard deviation distance from the average, add it and get a line, subtract from the average, draw a line, then you will find that as many as 68.26%. So roughly, if this line has been obtained or frequency diagram has been obtained by measuring 100 parts, then roughly about 68 parts will remain between these plus minus 1 sigma lines. About 95% of the points you will find within plus minus 2 sigma lines. You will find about 99.73 or all but 27 parts in 10,000 within plus minus 3 sigma lines. Okay, now what is the advantage of that? The advantage of that is that if you are in a process, you have a dimension, you measure the dimensions of certain number of samples. Say, for example, you have collected 50 samples and you take the standard deviation, you find out standard deviation by using a calculator, or you put it in Excel and find out sigma. Then you should be in a position to find out by plotting the histogram that whether it is following a normal distribution or not. There are other methods also. But the best part of that is that if you are able to draw a plus minus 3 sigma line, then that gives you a very good idea that over a period of time, whether your process is going to meet the required upper spec limit and lower spec limit or not. This is the advantage of having sigma. So as I told you, in a normal distribution, there are two parameters. What are those two parameters? One is average and the standard deviation. By getting average and the standard deviation, what are you getting? You are getting measures for upper control limit and lower control limit. How do you get that? On the average, if you add plus 3 sigma, you get upper control limit. On the average, if you subtract minus 3 sigma, you get the lower control. Now, what are they? Please notice that when you are calculating the upper control limit and the lower control limit, actually, you do not require any spec limit. Please understand that part, first of all. Spec limits are defined by who? Designers. And who is defining upper control limit and lower control limit? Your process. The way your process is, that is how you are getting your upper control limit and lower control limit. All that you need to calculate upper control limit and lower control limit are the dimensions which are collected over a period of time in a certain way. And then when you calculate that, you get the sigma and the average. One calculator is good enough for you to calculate. Then what? Then you will compare the upper control limit and lower control limit against the spec limits. If your upper control limit and lower control limit are within the spec limit, you will say the process to be capable. If your upper control limit and lower control limit are outside the spec limit, either one of them or both of them are outside the spec limit, you will say the process is not capable. And if a process is not capable, then what does it mean? It means that some of the products may have to be reworked and some of the product may have to be rejected. And that actually increases the cost of the process. So our job as engineer is to first of all find out whether a critical process which is running at the supplier end, that process's capability is there on. If you identify not capable process, particularly critical process, then your job as consultant, counselor would be how to bring those processes, make it capable. Okay. So process capability studies, basically, we come out with the determination of average and standard deviation. So as I told you that, first of all, come up whichever process you want to find out the process capability, find out the standard operating procedure of that process. What is standard operating procedure? How do you really set the process? What is the minimum training needed for operator to run that? What kind of tooling are used? Where from the tools are procured? Who is supplying the raw material or the input material for the process? Whether it is internally produced or whether it is coming from the supplier, whether those processes are under control or not, whether the material that is coming are within spec or not, whether its hardness, dimensions, surface finish, etc. are okay or not. So all those detailed study you have to do before you get into the collection of the data. That is a very, very important point for our understanding. Once you do that, you find that no, all the requirements are not being met. Then you have to sit with the supplier and then understand that how those out of specification as against the specification can really be brought back into within the requirement. Then only you can start the process capability study. Not that you just go and really delve into any process and then start collecting data. That is not going to serve your purpose. You must understand first process and the standard operating procedure, make sure the process is really working under the chance causes, and then you try to calculate the process capability. If it is not, you find there are too many assignable causes are present, even by technical judgment, you are able to see that. First, sit down, eliminate them. Try to take action by doing problem solving methodology. And once you arrive at a fairly reasonable conclusion, then no, my process is really working within the known factors, then you can collect the samples, draw the graph, ensure that it is a normal distribution or near normal distribution, and then you calculate your sigma and average. If you calculate the sigma and average by this method, that will be fairly, you will be able to conclude whether the process is capable or not. Otherwise, you know what will happen? You may calculate the sigma and average without doing all these things, and you wrongly conclude the process is not capable and ask the supplier to change the process. That will be very, very expensive and not really needed. So you have to help the supplier first to understand that whether basically the process is able to meet the specification or not by doing what I said just now. Now, there are two types of standard deviation. The first standard deviation is what I have written here on top, which is normally used in a calculator, or you will find that in Excel sheet also, this particular formula is written. This is called the sample standard deviation, the small s, not sigma. And the bottom is n minus 1. If you have collected total number of samples as n, so you have to divide at the denominator as n minus 1. So this is one way of calculating standard deviation. This standard deviation is a very realistic standard deviation. Now, those of you who have learned the process capability studies earlier, or those of you who have learned how to plot a X bar R chart, they would be knowing that one methodology of calculating standard deviation is collecting 3 to 5 samples in a short span of time. Say, for example, that in an hour, every minute, say one product is manufactured. Okay, one product is turned by the lathe machine, let us say, as simplicity. Then in 60 minutes, you are having 60 samples. Then over a shift of say 8 hours, you will be having roughly say 400 numbers. I'm taking out the lunchtime, tea time, etc. Say 400 numbers. So you have taken roughly one shift production for calculating the prosecutability, for doing the prosecutability study. Now, what I recommend strongly is that try to divide the entire time zone. Suppose you are studying the prosecutability study for 3 shifts. So what you do is that 25 subgroup you have to collect over 3 shifts. So what you do is that you subdivide the time in such a manner that at a fixed interval of time, you will be collecting roughly 5 consecutive samples. So how many samples you will be collecting? 5 into 25 is 125. So how will you plot? You write subgroup number 1 and write the dimension 1, 2, 3, 4, 5. Subgroup number 2, 1, 2, 3, 4, 5. Subgroup number 3, 1, 2, 3, 4, 5. Subgroup number 25, 1, 2, 3, 4, 5. For each subgroup, you calculate the average. So how many averages you get? 25. And then you take the average of the averages. We call it X double bar. But don't bother that. We are not going to use that much. For subgroup number 1, apart from average, you can also calculate the maximum dimension minus minimum dimension, that is range. So how many ranges you will get? Because you have 25 subgroups, you will get 25 ranges. Take the average of all the ranges. We call it R bar. Now, there was a statistician by name Mr. Patnaik, Indian, from Odisha. He came up with a range distributions, beautiful property. He found out that if that average of the ranges is divided by a constant called D2. What is D2? D2 is a constant. You can find the value of the D2 from the table against the sample size. Because in this case, I told you that there are 5 samples for each subgroup we have taken. So against n equal to 5, you can find the value of D2. If you divide the R bar by D2, you get an estimate of standard deviation. And that standard deviation is the ideal standard deviation, which may be completely different from this calculator standard deviation. This point, many people do not understand. More you streamline your process, more you try to remove the parameters or unnecessary factors from your process, you will find this standard deviation is nearing this standard deviation. If you have understood that, you will understand now the next topic, capability index, very simple. How? CP is nothing but upper spec limit minus lower spec limit. You don't have to do anything for the top part of CP. Why? Because that is decided by the designer or the customer. All that you need to do is sigma, standard deviation. So which standard deviation you are going to use here for CP? This standard deviation, R bar by D2. Not this one, not this one. All right. So that is the definition of CP. If this value, as I told you, that if this standard 6 sigma is nothing but the difference between upper control limit and lower control limit. What is upper control limit? X bar plus 3 sigma. What is lower control limit? X bar minus 3 sigma. So upper control limit minus lower control limit is what? X bar gets cancelled. So 3 sigma plus 3 sigma is equal to 6 sigma. So USL minus LSL, if it is numerically bigger than 6 sigma, your process is capable. If USL minus LSL is lesser than 6 sigma, your process is not capable. Okay. So ideally, about 1.33, if you get CP, it's a fairly reasonable process. If the value happens to be 2, it is a 6 sigma process. And what sigma we use here? R bar by D2. All right. See here, no target is coming in this entire formula. That means there is a fallacy here. If the entire USL minus LSL is totally away from the target and from the average and the actual process, it may so happen that you may still call it a capable process, because centering is not coming anywhere in the formula. Okay, I'll just explain you by a simple example. Let me come to that. So take for example that my X bar is equal to 0. My sigma 1 is 12. So what is my upper control limit? 0 plus 3 sigma. Sigma is how? What? Sigma 1, 12. So 0 plus 3 sigma is nothing but 36. 0 minus 3 sigma is nothing but minus 36. All right. I have not used anywhere specification limit. Only I have used the process as is. Now, let me try to put here the spec limits. Suppose the spec limit are also falling at the same line, that is nothing but USL is falling at plus 3 sigma and LSL is falling at minus 3 sigma. So your ratio of USL minus LSL divided by 6 sigma is 1. We call it Cp equal to 1. Now what we do? We make some improvement in the process. Keeping the average at the same 0. Suppose now standard deviation has reduced to 8. How do you reduce standard deviation? You have to make certain process changes. So here, spec limits have not changed. But what has changed? Standard deviation. So your Cp in this case is nothing but USL minus LSL remain 36 minus 36 is 72. And 6 sigma is nothing but 6 into 8, 48. So 72 divided by 48 is nothing but Cp is equal to 1.5. It's a capable process. Let's go further. I do some further work, and suppose standard deviation has become 6. The average remains same at 0. So in this case, what will be my USL minus LSL? Same, 72. And what will be my 6 sigma? 6 into 6, 36. So what is the Cp? 2. It has become now 6 sigma. I hope you are able to understand how by reducing the standard deviation, one may arrive at the 6 sigma and keeping the target by and large same. All right. What is the definition of CPK? The process capability index, okay, and with specifications around, okay. So process, that is why many people what they call CP as process potential index. They say that this is indicating the process potential, and CPK they refer as process capability index, CPK. So in this CPK also the sigma is same, but the formula is a little different. There, the capability index is actually divided into split into two parts. One is CPU, another is CPL. What is CPU? Here we are using X bar, that is average. What is average? If you remember this is average, what you consider as 0. That is all the dimensions that you have collected. If you take a simple average, that is the average you are talking about. So if you take that average, so USL minus the average divided by 3 sigma, whatever value you get is CPU. Then average minus LSL divided by 3 sigma, whatever value you are getting, we call it CPL. Whichever is the minimum of this, we call it CPK. So clear? CP does not have any reference of average. CPK has a reference of average. Otherwise, the sigma is same. USL, LSL is, of course, given by designer. Now, many people ask, what is PP and PPK? PP and PPK, all the formulas are same. CP can be replaced by PP if you are using the standard deviation as calculator standard deviation, all damage, no subgrouping, etc. 125 quickly taken samples, one after another, or maybe alternate samples, depending on the time span. And if you calculate it by calculator, instead of the standard deviation, which I said was R bar by D2, if you use this, you get what is called PP. And PPK, same formula as CPK, only thing, the standard deviation gets changed. I hope you are able to understand the basic thing. Now, a small case study. For a heat treatment process, the desired upper spec limit and lower spec limit are 49 and 41. Initial studies reveal the average to be 43.5 because I have collected about 100 samples and I took the sample average of the samples. it came out to be 43.5. And because I have taken R bar by D2, I took the standard deviation, I calculated the standard deviation as 2.5. So what is the upper control limit? Average plus 3 sigma. 43.5 plus 3 into 2.5 is 7.5, is UCL is equal to 51. And average minus 3 sigma, 43.5 minus 7.5 is 36. Okay. So let us look into this. So all the data of 100, I have arranged it on a table. Okay. Frequency distribution table. And if they're same, I have just made a stack pile, stack. And then I have joined the top line. I simulated a line. It is like that, like this. Now let us see how does my upper control limit and lower control limit falls. The upper control limit, which is I just now demonstrated to you, they are lower control limit 36, upper control limit 51, 51 and 36. And this is my average, which is coming somewhere around 43.5. This is my average. Okay. Incidentally, this is called voice of the process, not the customer, voice of the process. This is how the process is behaving right now. And my upper spec limit and lower spec limit are what? They are 49 and 41. And that is what is called voice of the customer. So voice of the customer is lower than the voice of the process. So is the process capable? No, definitely not. So if I calculate the CP, it turns out to be about 0.53. If you use if I use CPU and CPL, the calculation would show them as 0.73 and 0.33. So what is CPK? Lower of the two, 0.33. So always you will see that CPK will be lower than CP. And
Sir, this voice of a process is, these are the needs and satisfaction of desires of the customers, right, sir?
Voice of the customer is the desire of the customer. And voice of the process is nothing but the way the process is behaving right now.
But these are basically the needs and the wants of the customers.
Which one?
Voice of the process.
No. Voice of the process means if the process is allowed to speak, the process will tell you that, look, my dear friend, I am producing maximum this dimension and minimum this dimension. That is the voice of the process.
Can we say?
And voice of the customer is what the customer has expressed or what the designer, your designer, has written down in the drawing, that this is my upper spec limit, this is my lower spec limit.
Can we say?
Are you getting that?
Sir, can we say in other words that this is the capability to meet the customer satisfaction?
Which one?
Voice of the process.
No. For understanding the word capability, you have to compare the voice of the process to the voice of the customer. If your voice of the process is larger than voice of the customer, then you are not capable, because the process is producing here. For example, you see the process is producing quite a few dimensions over the spec limit on the upper side, and quite a few lower the spec limit on the lower side. So the process is not capable. Are you able to see this?
Yes, sir.
Yes. So voice of the process is as is the process is producing, as is, without doing any change. If you go to any process and collect the samples and measure the sample and then plot and then calculate the X bar and 3 sigma and then find out X bar plus 3 sigma, X bar minus 3 sigma, you get what is called the control limits. And they are called the plus 3 sigma, minus 3 sigma. They are called the process voice of the process. And for understanding voice of the customer, you don't have to go to the process even. You just go to your drawing. The drawing will tell you the spec limit for that particular dimension. They are the voice of the customer. If your voice of the customer is higher than the voice of the process, your process is capable. For example, in this case, since the Cp and Cpk value is less than 1, so therefore the process is not capable.
Capable, right.
Let us now do the next part. That means what we do is that we do some now changes. What we do, we work on the heat treatment process. We found that quite a few tray diameters, etc., they are actually far away from the main heating area, and therefore there the hardness is relatively on the lower side. It is not getting hardened, And therefore, what we did some modification on the heating coils, we did some modification on the heating trays, the atomizer, etc. We made an improvement, etc. And then we found that yes, we are able to now reduce the variation. So the variation has now been reduced. So the new process, this is the new voice of the process. What is the new voice of the process? New voice of the process is plus 3 sigma and minus 3 sigma. Standard deviation is 1. Earlier, how much it was? 2.5. Now it is what? 1. So my voice of the process is defined by upper control limit, lower control limit. My average is 45. So 45 plus 3, 48, and 45 minus 3 is 42. And if you see now, the voice of the process is lower than the voice of the customer. Therefore, my process is now capable. And if I calculate that in terms of Cp and Cpk, how much it is? 1.33. Cpk is also 1.33. Why? Because the target, that is nothing but the 45, and the USL plus LSL divided by 2, that is target, that is also 45. So therefore, Cp becomes equal to Cpk. Both are 1.33. Okay. So, any question?